Yeah, welcome. So the topic we'll be discussing in this lecture is hashing. This is a fresh topic with what we have discussed in the last class. With that, we'll stop discussing searching and sorting techniques. And now we'll be moving to the next topic. It is hashing. Okay. So before discussing the actual topic hashing, first let us try to understand why should we discuss hashing, or what is the motivation behind discussing this topic hashing. Okay. So the reason why we are discussing hashing is if you consider the operations like insertion, search or deletion in a binary search tree, it will take order of n times. That is the time complexity is order of n. But in case of a balanced binary search tree like AVL tree or a red-black tree, the time complexity is order of log n. Is there any other way to reduce the time complexity further? That is the question. Can we reduce the time complexity further less than log n? Is it possible or not? Yes, it is possible by using a technique called hashing, right? So that is the reason behind discussing this topic called hashing. So not only with respect to BST and balanced BST, if you consider sequential search, if you take sequential search, what is the time complexity of sequential search? The time complexity is order of n. Okay. And what's the time complexity of binary search? A binary search should have a sorted list, so its time complexity is order of log n. So for searching an element from a list of elements or from an array, so this is the so far whatever we have discussed, this is the least time complexity that is achieved through binary search. But can we reduce it further? Yes, we can reduce it by using hashing. So by using hashing, the time complexity will be just order of 1. It will be just order of 1. That is with one operation you can identify. With just one move, with just one move, you can identify the place to which the new element to be inserted, or you can identify the element that you are searching just by performing one single calculation, or the element you want to delete, where it is you can locate it in just one operation. Okay, so it takes only one operation to perform insertion, searching or deletion. So that is the reason why we are going to discuss about this hashing techniques. Okay, so basically what is a hashing, or how do we define hashing? So in the simplest term, hashing can be defined something like this. In the simplest term, hashing can be defined something like this. It is a concept of mapping key. It is a concept of mapping keys, concept of mapping keys to a particular position, to a particular position in the list or in the array. Okay, so given a key, where it should be placed in the array. Okay, so that is what the hashing is going to do. So hashing is the concept of mapping key to a particular position in the array or a list. Okay, so for example, if you have an array, say the size of the array is 10, that is it can hold 10 elements. So the index is like 0, 1 up to 9. Okay, now say for example I want to place an element called 25, then we will apply this 25, this 25 is called as key is 25. Okay, so this 25 will be given to a hash function. We'll have a hash function of the form h of k. Okay, the h is a function which is called as hash function. This function will take the key as input. It will take the key as input and it will produce any one of these values as output, because now our array size is what, 10, that is starting location is 0 and ending location is 9. If this function returns 7, then this element 25 will be placed at 7th location of the array. Okay, are you getting? Say there is some other key value. Say key is 45. Okay, now you give to the hash function. For example, if it returns 2, then that element will be placed in the second location of the array or list. Okay, so how it is going to work, all those details we'll be discussing soon. But I'm trying to uh, make you understand the definition of hashing. So this is why we define hashing something like this. So hashing is the concept of mapping key to a particular location or position in the array. Okay, instead of position you can also call it as a, or call it as location. So it's the concept of mapping key to a particular location in an array or in a list. Okay, right. So before going to discuss the actually hashing, whatever in the book style, before going to discuss that, I'll be giving you a brief overview on hashing. uh, I'll be trying to make things as simple as possible with this overview. Okay, so let us assume that we have an array or a list. Okay, let us assume we have an array or list of size 10. Okay, so the size is 10, this list size is 10. So 1 2 3 4 5 6 7 8 9 and 10, 9 and 10. So this array is indexed 0 1 2 3 4 5 6 7 8 and 9. It's indexed like this. Let us call the array as A. Let us assume the name of the array is A. Okay, it is called as A, right? Now let us see how hashing is going to work with this particular example. With this example array, let us try to understand how hashing is going to work. Okay, so in hashing we know that we need a hash function. So to perform hashing, first we need a hash function. So what is hashing? Mapping keys to a particular location. So hashing is, it's the concept of mapping keys to location in an array. Okay, I'm keeping it short, in an array, right? Now we need a hash function. Now we need to perform hashing, we need a hash function. Okay, so let us assume that we have a simplest hash function of this form. This is the simplest and the commonly used hash function. Okay, so what this hash function says, in the sense, what this is the hash function key, it it key modulo yum. Okay, key modulo yum, where yum is nothing but the size of the list or size of the array. Okay, where yum is nothing but the size of the array. Okay, so in our case, what is the size of the array? In our case, the size of the array is 10. So which means that this is our hash function. The hash function is key modulo 10. Okay, this is the hash function, right? Okay, now let us take some values and let us see how these values will be placed in the hash table. Okay, so this table, which is generally an array, but in the context of hashing, this table will be called as hash table. Okay, so let us take some values. Say let me take 5 2 7 25 36 47. Okay, these values, let us see how it will be placed. Okay, so these are the key. So first k1 is what? 5. So perform 5 modulo 10. What is 5 modulo 10? 5 modulo 10 is what? 5. It is just 5. Okay, the remainder is 5, right? It is modulo, right? It is not a division, it is modulo division. Okay, so, or this is quite misleading. right? So I'll write mod here. It is not normal division, it is modulo division. Okay, right. So it is 5 key mod m is 10, so key mod 10. Okay, so 5 modulo 10, it is 5, remainder is 5. Okay, so it means that this 5 is placed, should be placed at the fifth location in the hash table. So this 5 will come here. Next element is what? 2. So what is 2 modulo 10? 2 modulo 10 is also 2. So it means that this should be placed in the second location. So it is mapped. This key is mapped to fifth location. This key is mapped to second location. Next the key is what? Third key is 7. 7 modulo 10 is also what? It is 7. So this key 7, it is mapped to 7th location. Okay. Next 25. 25 modulo 10 is what? 25 modulo 10 is also 5, right? Because 10 twos are 20 and remainder is 5. This is also 5. Okay. Now this 25 should also come in this location. Okay. But actually this location is already occupied. Actually this location is already occupied. So this is called as collision. So this is called as collision. So when you are performing hashing, this is one of the problem you will face in hashing. So this problem is called as collision. So how to deal with the collision, let us discuss later. Okay, but there is a problem. So normally in hashing we will encounter this problem called collision. What is collision? Two or more keys may map to the same location, that is called as collision. So here if you see, key 4 and key 1 are mapping to the same location. So this is called as collision. So when a collision occurs, how to handle that I will be explaining shortly. So just let us understand that this is creating a collision. I am not mapping this now. I am keeping this hold. Okay. So let us see the next key. Next key is 36. So 36, again hash function 36 mod 10 is what? 6. 6. Okay. 10 threes are 30, remainder is 6. So it means that this 36 should be mapped to sixth location. Okay. Next is 47. Next is 47. K6 is 47. Again if you see, 47 mod 10 means what? 47 mod 10 is what? It is 7, right? 10 fours are 40, the remainder is 7. But already 7th location is mapped to key 3, which is 7. Okay. So again this is also creating collision. Okay. So generally this is how we perform hashing. Okay, this function may vary. Here I have taken the simplest hash function. This is the simplest and the most commonly used hash function, which is key modulo the size of the hash table. Okay, but there are several other hash functions also available. You can use any hash function. I mean, in the if you are getting this type of problem, the hash function will be given. If the hash function is not given, if no hash function is given, then you have to assume that this is the hash function. Okay, otherwise the hash function will be given. Okay, fine. Now, now the common problem that we will face with hashing is what? Collision. Now let us discuss how to deal with this collision. So basically there are two ways of dealing with collision. Okay, the first method is called as, so collision is handled in two ways. Okay, the first method is called as linear probing. The first method is called as linear probing, and the second method is called as chaining. These are the two ways of handling collision. Okay, the first method is called as linear probing and the second method is called as chaining. Okay, so let us see the first method first. First method is linear probing. So using linear probing, how these collisions will be handled, let us see. Okay, so now let us assume that this initially we are getting collision with 5. Okay, so let us assume that this is not mapped, that is key 5 is not mapped, and also let us assume that key 6 anyway it is not mapped. Okay, so key 5 is not mapped and I will delete this. So when you are trying to map key 4, we are facing collision. Okay, now what we are going to discuss is how this collision will be handled by using linear probing. That's what we are going to discuss. Okay. So key 4, when we try to map key 4, it is mapping to fifth location, but already the fifth location contains some other value. So this is called as collision. Now where to map key 4? So the concept of linear probing, what it says in the sense, you just to go to the next location and check whether that location is what you call, whether that location is empty or not. If that location is empty, just use that location. Okay. So now if you go to the next location, it is sixth location. Is it empty or not? Yes, yes, it is empty. So use that location. So which means that key 4, that is 25, will be stored here. If it is not empty, you have to go to the next. If it is not empty, you have to go to the next. If it is not empty, go to the next. If this is also not empty, then go to the top. Okay. So how it will be done? So how it will be done in the sense, whatever the result you got here, whatever the mapped value you got here, okay, right? Say let us call this as R. So what you have to do is continuously you have to do R plus 1 modulo 10 or modulo m. Okay. So in our case R is 5. So when there is a hashing, you have to do this. So R is 5. So it means that 5 plus 1 modulo 10. So what is 5 plus 1? 6. 6 modulo 10 is 6. So go to the sixth location and see is it free or not. If it is free, use it. If this is also not free, again repeatedly do. 6 plus 1 modulo 10. 7 plus 1 modulo 10. So on and so forth. Right. Now as this is free, we will use this. Okay. But now we have another problem. See, K5. Now we have to map K5. So what is K5? K5 is 36. 36 modulo 10 is what? 6. It should be mapped to the sixth location, but already sixth location contains some other value. So what you have to do, again apply this logic. Now R is 6. So 6 plus 1 modulo 10, that is 7 modulo 10 is what? 7. 7. But if you see, seventh location is also occupied. So again there is a collision. So once again continue this. So until you find an empty location, you should continue. So 7 plus 1 modulo 10. What is that? That is 8. Okay. Go to the 8th location and see. Is it empty or not? Yes, it is empty. So 36 will come here now. Are you getting? Right? Now locate key 6. Okay. So now we have to map key 6. So 47 modulo 10, which is equal to 7. But 7th location is already occupied. There is a collision. So what you have to do? Again perform this operation. That is linear probing. 7 plus 1 modulo 10. That is next location you have to check, which is 8. Is 8th location is free? No, it's not free. So again check the 9th location. So how you will get 8 plus 1, whatever the previous location, plus 1 modulo 10, which is 9. Is this is free? Yes. So 47 will come here, right? Okay. Say that now I want to insert something called, say, 59. Okay. Now if you map 59, what will you get? If you map 59, what will you get? You will get 9, right? You will get 9. So I'll delete this. So if you map 59, that is, it is 7th key, you will get 9, but already 9 is occupied. Okay. So just I wanted to show when it reaches the end of the table, what will happen. Okay. So key, this is key 7. 1, 2, 3, 4, 5, 6, 7. So key 7 is what? 59. 59 modulo 10 is what? 9. Okay. But 9th location already occupied, there is a collision. So what you have to do? 9 plus 1 modulo 10, which is 10 mod 10, which is nothing but 0. So if you reach the end of the table, it will go back to the beginning. Okay. So if the 0th location, is it already occupied or not? No. So this hash value, this key will come here. Okay. So on and so forth. So like this, you can keep inserting keys until the table becomes full. Okay. When the table becomes full, you have to reallocate memory, right? After reallocating, but if you reallocate memory, say for example at one point of time the table becomes full, so that all the 10 values or some 10 values are occupied, then you have to allocate, say you are doubling the table, instead of 10 you are making 20, but after making 20 then you have to recalculate the hash value for every key, even for the key that is already located. Okay, because now this mod value is changing. Previously, what is yum? Previously yum was 10, but now when you increase the table size it will become 20. So whenever you increase the table size, the what you call the home location, this is called as the home location of the values, the home location of the key values will change. Okay, so so everything should be recalculated. Okay, so this concept is called as linear probing. So that is whenever a collision occurs, we will just to go on to the next location and check whether that location is empty or not. If there is a empty space, we will insert. So we will continue this process until the table is not full. Okay, if the table is not full, we will find an element and we will insert. If the table is full, then you have to double the space of the table. Okay, or you have to allocate some more space, right? But normally the researchers or the scientists suggest that you should not wait until the table becomes full. When the table reaches 0.75 amount of table, if 0.75 amount of table is filled, that is if 75% of the table is filled, then by that time itself you should allocate more spaces, right? But whenever we increase the space for the hash table, the what do you call the every key should be once again rehashed, so that is called as rehashing. For every key you have to calculate hash value again, and once again you have to place it in appropriate position. Okay, right? So this is how what you call linear probing works. So next what we are going to discuss is, next we are going to discuss about chaining, how chaining is going to work. Okay, so let us take an array. So linear probing and chaining both are the techniques which are used to resolve collision. Okay, so these are techniques which are used to resolve collision. So let us take an array of size 10 or list of size 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, say now these are the values we want to insert. Say 2, 5, 9, 12, say 15, 19, 32, 45. Okay, let us assume these are the values we want to insert. So the first is what? K1. K1 is 2. So 2 modulo 10 is what? 2. So it should be mapped to the second location. So 2 will come here. Next K2 is what? 5. So 5 modulo 10 is what? 5. So 5 will come here. Okay. Next K3 is what? 9. So 9 modulo 10 is what? 9. So 9 will come here. Okay. Next K4 is what? 15. 15 modulo 10 is what? 5. 5. So now 5 is already occupied. So here it is creating what? It is creating an collision. So now we are discussing about what concept? Chaining. Now we are discussing about chaining. Okay. So the concept of chaining, what it says in the sense, every location of this hash table is not only, it can not only hold a value, but it is a key and a pointer pair. It is something like a, each location is something like a node in a linked list. A node in a linked list contains what? It contains a data part and a pointer. Okay, so in the data part it is 5. So now there is a collision, so it has a pointer. So using this pointer, this pointer can point to another node of the same type which contains a data part and a pointer. Okay, so another node will be created, and this particular entry's pointer will point to that node, and in that node's data part will keep this new value. What is the new key? 15. Okay, and time being this pointer will be null. This pointer will be null. Okay, so this is how we place 15. Okay, so this technique is called as chaining. Next we want to position 19. Okay, so 19 I'll write here. So K5 is 19. So 19 modulo 10 is what? 19 modulo 10 is 9. Again, ninth position is already occupied. So again, what should you do? We should do chaining. Okay, so the ninth positions pointer we should use, and using that we will let it make it point to another node, and that node's data part will now hold 19. Okay, and this node's next will be currently null. So next value that we want to insert is K6. So K6 is what? 32. So 32 modulo 10 is what? 2. 10 3s are 30 and remainder is 2. Okay. So already 2 is filled. There is a collision. Now again use the pointer part of this particular entry and let it point to another node, and this node's data part will now contain 32. Currently it will be null. The next pointer of 32 will be null, and the next value is what? K7 is 45. So 45 modulo 10 is what? 5, but 5 is already collision. Okay, so see its next pointer, 5's next pointer is pointing to 15. Now 15's next is null, so let 15's next point to another node. Okay, and in that data part we'll keep 45. Okay, so like that you can add any number of nodes, right? So this concept is called as chaining. So this is also one of the technique for dealing with collision. Okay, in linear probing what we do, we just linearly search the next position, and we, if the next position is empty, we will place the key there. But in chaining we do like this, we form a chain. So it is like a chain, right? We form a linked list which is similar to a chaining. Okay, right? Fine. So this is the overview of what we are going to discuss in this lecture. Okay, right? So now let us discuss the actual concepts, right? Okay, so for example, so here we are going to, so whatever I have explained now, I have explained directly key and mapping the keys to the array locations. That is how we have discussed. Okay, but actually in the book it was how it is mentioned, in the sense we will consider every entry, as a pair of item. Okay, we will consider every entry as a pair of item, or we'll consider every item as a pair. Okay, this pair contains what? This pair contains key and a value. Every item will have a pair, and this pair contains key and a value. Okay, right? So there will be a key part and also there will be a value part. So why we are considering like this, in the sense, in several applications this key value pair will be there. Say for example in dictionary. In dictionary, uh, dictionary is also a data structure. Okay, there is a data structure called dictionary. In Python you might have learned. So dictionary data structure contains, it is of what format? It is of this format, key and value format. There will be key and associated value. Okay, so dictionary, this is as a data structure. But generally if you see dictionary also, what the normal dictionary which we use for finding the meaning of a term, it is also of what type? It is like a key and a value, right? Say for example, you want to find the meaning of something, apple, it's a fruit, it is in red color, something like that. In the dictionary it will be available. So what is this part? This is key and this is value, right? Or something else you want to find the meaning in dictionary. Say for example, you want to find what is meant by hash, what is meant by hashing. So there will be some meaning, right? It is a form of mapping or something like that. Something will be there. Now this is a key and this is a value, right? Okay. Or you are searching like what is sorting in dictionary. So it is arranging things in order. So this is a key, this is a value, right? Okay. So there are several places in the real life and also in computers we need uh, items to be stored in the form of key and value pair. Key and a value pair. Okay. Or for example, if you take a symbol table in the sense, in the context of a compiler, if you see a symbol table, like symbols in the sense, what in a program, whatever the variables or keywords that we use, that is called a symbol. So for example, in a typical program, I'm using like this: int a, float b, okay, something like that I'm using. So printf hello. Okay. Now for this, a symbol table will be created. The compiler will create a symbol table. Whatever we are using, it will create a symbol table. Int, it will specify that it is a keyword. Int, it will specify that it is a keyword. And next a, it will specify it is an identifier. Identifier means it is a user defined variable. Again float, it will represent it as keyword. Okay. The compiler will do all these things. And b, again it will be called as an identifier. Okay. Printf, it will say that it's a library function. It's a library function available in some header file or whatever it may be. And hello, it's a string. It's a string identifier. It's also an identifier, but it is given by the user, string, right? So it's of type string. Okay. So this is called a symbol table. This is called a symbol table. The symbol table is also what format? It is a key value format. What is this? Is a key, and these are the value corresponding to that key, right? So in several places. So what I'm trying to convince you in the sense, in computers, in several places we use data structures, or we use data items in the format of key value pair, right? So we are going to discuss hashing, not with directly with a key, but with a key and a value pair. Okay. Given a key and a value pair, uh, you will use hash function on key only. Given a key and a value pair, so we will be given, say for example, you have several items. Okay. You have several items, and each items contains what? Each item contains a key and a value. Each item contains a key and a value: k1 v1, k2 v2, k3 v3, so on and so forth up to kn and vn. That is, each item contains a key and a value, right? So this is item 1, this is item 2, this is item 3, this is item 4, and this is item 5. Now each of these item we have to map. Now each of these item we have to map into the hash table. Okay. But for mapping we will not use the values, we will use only keys. So using this key k1, we will map this item into the hash table. Okay. So whatever the result of the hash table, in that location it will be mapped. Similarly, using this key k2, this item will be mapped into the hash table. Using this key k3, this item will be mapped into hash table, so on and so forth. Like that we will map every item to the hash table. So for mapping an item to the hash table, we are not going to just consider only key. We are not just going to map only key, but we'll be mapping an item which contains key and value pair, but mapping will be done based on keys, right? Okay. So what are the typical operations uh, that we can perform on a hash table? Okay. So what we can perform in the sense, we can determine if a particular value is in the hash table or not. Okay. We can retrieve the attributes of the name. We can modify the attributes of that name if it is there. We can insert a new name. Okay. Given a key and a value in the sense, instead of value you can call it as name. Given a key and a name, we can insert a new name into the hash table. We can delete an existing name from the hash table. Okay. So these are the typical operations that can be done on a hash table, right? Okay. So this is the ADT, abstract data type, for what you call for symbol table. Okay, symbol table. So here symbol table means it's a key value pair. Okay, why we are calling as a symbol table? Because it's not going to have the symbol table, in the sense it's a table with key and a value pair. Okay, that's it. It contains ki and vi. It contains keys and also it contains values, right? Okay, so you can generically you can call it as a hash table also. So this hash table now not only contains values or keys, it contains both key and value pair, right? Okay, so the ADT of a symbol table is given like this: creating a symbol table. Okay, and to check is in name, whether a particular name is in the symbol table or not. If the name is there, it will return true, otherwise it will return false. Find, attribute find. Okay, if that particular name is there, then it will return the corresponding attribute, otherwise it will return null. So the name may be connected with more than one attributes. If there are more than one attributes, it may return those attributes. Okay, then insert. This is to insert a name and its attributes. Okay, right? So what does it mean? In the sense, for a key, it is not that only one values. For a given key, you can have more than one values also. Okay, so each of the values you can consider as attribute, right? And then delete. So delete symbol table name. So from the symbol table, it will delete the entry which contains this particular name, right? So the typical operations that we perform are search, insertion, and deletion. So for searching, what we use the keys. Okay, and we perform I mean, in search tree, in binary search tree kind of thing, we'll use the key and we will compare, right? But in hashing method, what we'll use is we'll use a hash function. Okay, in binary search tree, we use what we do, we compare with the key whether whatever you want to search, whether it is equal to the root node or not. If it is not equal to the root node, then you check whether it is less than the root node. If it is less than, then go to the left subtree in case of binary search tree. Otherwise, go to the right subtree. Like that we do, right? So that is how we do in search tree, in binary search trees. But in hashing, what we do is we use a hash function. Okay. So there are two types of hashing. One is called as static hashing. The other one is called as dynamic hashing. We are going to discuss only about static hashing. We will not be discussing anything about dynamic hashing. Okay. So this is a typical hash table. So a hash table can have several rows. Okay. So here we are assuming that the hash table contains b rows. The hash table contains b rows. That is, it is starting from 0 to b minus 1. Totally, there are b rows. Okay. Each of these rows is called as buckets. Each of these row is called as a bucket. Okay. So this is one bucket, this is one bucket, this is one bucket. Like that, we have b buckets, and these buckets are numbered from 0 to b minus 1. Right. Okay. And each bucket can hold this many slots. Each bucket can hold s slots. These slots are numbered from 1, 2, 3 to s. Okay. So what does it mean? It means that each entry in this hash table, each entry in this hash table can hold s values. It's not just one value. Each entry can hold how many values? S values. Okay. So in a typical array, we discussed that each location in an array, each location can hold only one value, right? But if it is an, what do you call, but now we are extending that. If it is a two-dimensional array, say you have a two-dimensional array, okay, of two rows and n columns, then each row, sorry, of two columns and n rows, then each location can hold how many items? Two items. You get it? That is what this s is. S is number of slots. Okay. If you have five columns, now what will happen? Now each row can hold five values. Okay, five values. So that is called a slot, right? Okay. So a hash table, each row in the hash table will be called as bucket, okay, and each row can hold some S items. So if a row can hold S items, then it means that there are S slots, right? Generally S will be 1. So whatever we have discussed previously there, S is 1. There are some terms like identifier density. Identifier density of a hash table is given as n by t. Okay, identifier density of hash table is given as n by t, where n is the number of identifiers in the table and t is the possible identifiers. See, n is the number of identifiers means currently how many identifiers are there. That is called as n. Okay. Say for example, what in the previous case we have discussed, there is a hash table with 10 entries, I mean with maximum 10 locations, and we placed some values. Say for example, I am placing the values 2, 6, 8 and 10. Okay. So 2 will be placed in some location, 6 will be placed in some location, 8 will be placed in some location and 10 will be placed in some location. Currently the hash table contains how many values? These values 1, 2, 3, 4, 4 values. Okay, so that is called as n, the number of identifiers in the table. Currently how many identifiers are there? 4. T is the possible identifiers. See, possible identifiers means actually in this case there is no limit. Possible identifiers means it is all integers. It is all integers. So maybe if you are using integer data type to represent this, then it is 32,767, which is the highest integer possible. With uh, uh, that also with I think with what do you call, with 2 bytes. Okay, if it is 4 bytes, if it is 4 bytes, then the highest value is what? It is 2 to the power 32, right? 2 to the power 32, but we have to consider the negative direction also. Okay, 2 to the power 32. So mm, so it will be a huge number, right? It will be a very big number. So let us assume that it is a 2 byte, the integer is 2 bytes. Okay, then it will go up to how much? 32,767. These are the different possible values. Then it means that identifier density is 4 by this. Okay, so if you calculate identifier density like this, then what will happen? uh, the possibility of collision is high. The possibility of collision is high because what? Because why? Because our range is too high. The range, the possible values is too high. Okay, so obviously there will be collision. But this is how we calculate identifier density, the number of identifiers and t possible identifiers. So normally t will be very high. Normally t will be very high, and that is the result of collision. That is the reason for collision. Okay, and load density or loading factor is calculated something like this: alpha equal to n by s into b, where s is the number of slots and b is the number of buckets. Okay, s is the number of slots and b is the number of buckets. Okay, say currently there are n items. Currently, so n is what? N is the number of identifiers in the table. Okay, assume that again assume the same table. Assume the hash table contains 9 entries, 0, I mean 10 entries, 0 to 9. Okay, so in this case there are how many buckets? This is one bucket, this is one bucket. There are totally 10 buckets. Okay, number of buckets is 10. B is the number of buckets, which is 10. S is the number of slots. Each slot is having how many buckets? I mean each bucket is having how many? This is bucket B0, this is B1 up to B9. Bucket B0 is having how many slot? Only one slot. Each bucket is having only one slot. Okay, so S is the number of slots per bucket. Okay, so number of slots in a bucket. Okay, so 10 into 1 is what? 10. Okay, n is, let us assume as usual 4 entries are there. Some 2, 5, 8 and 10 are placed. Okay, so it is what? 4 by 10. 4 by 10 is what? 0.25. Currently this much load is there. 0.25 load is there. Are you getting? Right? assume that the number of slots is 2. Number of slots is 2 means in each location we can hold two values. In each location we can hold two values. Okay, but now also assume that the hash table contains only 5 values. Okay, so n is 5, still n is 5, but s is now 2 and b is 10. So now it will be what? It will be 4 by 2 into 10, that is 4 by 20. Okay, now it will be 4 by 20, right? So what is 4 by 20? In this case it is 4 by 20, okay, which is 0.2. Okay, 4 by 20, which is 0.2, right? So this is how we calculate loading density, right? Okay, so what is meant by, so here there is explanation. So the point is the number of the chances of collision is high, since the number of buckets B is usually several orders of magnitude lower than T. The number of buckets will be very much lower than T. What is T? T is the set of possible identifiers, the total number of possible identifiers. Okay, since the number of buckets B will be very much less than T, the hash function must map several identifiers into same bucket, which will result in collision. Okay, two identifiers, or instead of identifiers you can call it as keys. If two keys I and J are synonymous with respect to F, two keys I and J are synonymous. When we call it as synonymous, if f of I is equal to f of j, or instead of f of I you can call it as h of I, which is a hash function. If h of I is equal to h of j, okay, that is the result of h of I is some say some q, then h of j is also q. It means both these keys are mapping to the same location. Okay, both these keys are mapping to the same location. Then we say that I and j are synonymous, that is they are going to map to the same location. As a result they will create collision. Okay, right? Okay, so here are the two terms which is defined. One is overflow, the other one is collision. An overflow occurs when we hash a new identifier into a full bucket. So the question of overflow comes when what you call, when the bucket contains more than one slot. Okay, if each bucket contains only one slot, then both collision and overflow are same, right? But anyway I'll try to differentiate collision and overflow. Say for example, we have a hash table something like this. Okay, say the hash table contains 0, 1, 2, 3, 4, that is 5 buckets, and each bucket contains two slots. Okay, now assume that this bucket contains some value, say say it contains 10, say this contains 21. Okay, say this is empty, say this contains 33, right? Something like this. Okay, now say for example you want to insert 43. Now if you want to insert 43, okay, let us assume this total size of this is 10. Okay, let us assume total size of this is 10 up to 9, 0 to 9. Okay, so 43 mod 10, you have to perform 43 mod 10. Okay, 43 mod 10 is what? 3. So if you see the third location, actually there is a collision. But it is not overflow, because one slot is filled, another slot is empty. Okay, so this is called as collision but not overflow. So this is how we differentiate collision and overflow. And overflow occurs when we hash a new identifier into a full bucket. So this bucket is not yet filled. This bucket 3 contains two slots. Only one slot is filled, another slot is not filled. But what is collision? A collision occurs when we hash two non-identical identifiers into the same bucket. 33 is also mapped here. 43 also mapped to the same bucket. But there is a place, so we can map 43 also. Okay. So even though there is a collision, in this case there is no overflow. Right? But assume that again you want to map 63. 63 mod 10 is what? 3. Now can you map? Now if you map, now there is a collision and also there is a overflow. Okay, so this is how we differentiate collision and overflow. So collision occurs when we hash two non-identical identifiers into the same bucket. Okay, and overflow occurs when we hash a new identifier into a full bucket, right? But when the number of slot is only one per bucket, in each bucket if you have only one slot, then whenever there is a collision there will be overflow, right? So assume this case 0, 1, 2, 3, 4. Okay, assume up to 9, 10 entries are there. So now 33 is here. Now if you want to insert 43, already in this bucket can contains only one slot. 43 you cannot insert. So now it is a collision and also overflow, right? Fine. So here is some example it is given. Say for example, these are the values. These are some of the library functions in C. For this function, for these we want to insert into the hash table. Now this is our hash table. Okay, this hash table contains 25 buckets or 26 buckets. This hash table contains 26 buckets. Okay, why 26 means depending on the number of alphabets. English alphabets contain 26. So here the hash function is little different. So it contains 26 buckets which is starting from 0 to 25, right? Now these are the what you call these are the functions these are the functions which you want to map into the hash table. Okay, so how we map in the sense the mapping function is here, the hash function how it is given in the sense take the first character. Take the first character. If the first character is A, map to 0th location. If the first character is B, map to first location. If the first character is C, map to second location. If it is D, map to third location. If it is E, map to fourth location. If it is F, map to fifth location. If it is G, map to sixth location, so on and so forth. If it is Z, map to 25th location. So that is what now the hash function is. Okay. So these are the what you call functions which you want to map to the hash table, and this hash table contains two slots. Each bucket contains two slots. Okay, so totally the hash table can hold how many entries? There are 26 buckets and each bucket can hold two slots, so there are 26 into 2, it can hold 52 entries, right? Okay, so first is a cos. So it's what is its starting term? A. So it will be mapped into this 0th entry, so it comes here, right? Next is define. So define starting term is D, so it will be mapped. D means it will be mapped to which location? Third location, so define comes here. Next is float. Its starting character is what? F. So if it is F, it will be mapped to fifth location, so it comes here. Okay, next exp. Exp starts with E. If it is E, it will be mapped to fourth location, so it comes here. Next is character. It starts with C. C, it will be mapped to second location, so it comes here. Okay, next is a tan. It starts with A, so it is supposed to map at 0th location, but in 0th location already there is a cos. So it is a collision, but it is not a overflow. It's a collision, but it is not overflow because there is another slot. So in this slot we are keeping a tan. So these two are synonymous now. A cos and a tan are synonymous because they are mapping to the same location in the hash table. Next is seal. Take the first character C. So it is mapped to the second location, but already it contains character, this particular thing. So there is a collision. Okay, but again even though there is a collision, it's not an overflow. So this seal can be placed here, right? Okay. Next is what? Floor. Okay, floor is F. It starts with F. So it should be mapped to fifth location, but already there is another entry here. So there is a collision, but still there is not overflow. So this can be placed in this second slot. So it comes here, right? Next is clock. Clock stands for C. Clock stands for C. Okay. Now if you see, that is C maps to second location, but already there is a character and seal is there. So now there is a collision and also overflow. Now there is a collision and also overflow. Okay. So we are not currently mapping. We are not discussing now how to deal with map overflow, even though I have told you briefly. but currently we are not considering this as there is a overflow, right? Next is what? C time. Again, if you see C time, it should map to this location, but already it is full. There is a overflow, so we are unable to map this C time also, right? Okay, fine. So now these hashing functions, what are the various ways of the this? So here we have used a simple hashing function, something like A is mapped to 0, B is mapped to 1, like that, up to Z is mapped to 25. But generally we should actually it is a crucial task in defining the right hash function. Okay, so the hash function should be such a way that it is easy to compute. It should not be, the hash function should not be a very complex one. It should be simple enough to compute. Okay, and also it should result in minimal number of collisions. It should not create many collisions. It should create as less collisions as possible. Okay, so there are many methods. There is a method called middle square method. We are not going to discuss this. And the commonly used method is division method, which we already discussed many times. So in division method, whatever the key will perform modulo divide by m. Okay, so so whatever we have discussed so far, if key is 25, then 25 modulo m. Okay, if m is 10, then it is 25 modulo 10 is 5, right? Okay, or sometimes you may be given some function like this. Okay, like 2 into k plus 3. Okay, in that case what you should do, whatever the key is, if key is 25, then multiply 25 with 2, 50. 50 plus 3 is 53. Okay, now 53 you do modulo 10. 53 modulo 10 is 3. Okay, if this type of function is given, then you have to follow this technique, right? Okay. So generally mostly we'll be using this division method, or in some cases in exams you may get this type of questions. Okay, right? Map the following values using the following hash function 2 into k plus 3. Then you have to apply m also will be given. Okay, if m is 20, then you have to do modulo 20, right? Okay, so this is how this works, right? Mm. There are some other ways of hashing. Hash functions are available. Let us have a brief intro to that. So there is another technique called as folding techniques. So in folding technique, what we do in the sense, in folding technique there are two, basically it partition the entire identifier into several parts. Okay, and then it uh, all all except the last one will have the same length. Okay, given a long identifier, it will break the identifier into several parts of equal size, right? But but when you break like that, every part will be of equal length except the last one. For the last one we cannot guarantee, it may be of equal length or it may not be of equal length. Okay, then we add all these things, and as a result whatever we get, that will be considered as the mapping value, right? Okay, say for example, there are two ways of this folding techniques. One is called as shift folding, another one is called as folding at boundaries. So let us see how this shift folding works. Assume that this is the key which you want to map. Of course it's a long number, 123203241112220. This is the key or the identifier which is to be mapped. Okay, now we divide into certain number of partitions. Okay, let us assume the partition size as 3. Let us assume the partition size is equal to 3. So which means we have to divide into, so divide this into several smaller partitions such a way that the individual partition size will be maximum of 3. Okay, so the first partition will be just 1 2 3, so that we got this 1 2 3. Second partition will be just 2 0 3, we got this. Third will be 2 4 1. Fourth will be 1 1 2. Okay, now the last partition we cannot guarantee, it may be of equal size or it may not be of equal size, so it is just 2 0, so 20, right? Now you add all these things. If you add all these things, what you get is 699. So it means that this value should be mapped to this address 699. Okay, right? So this is what this shift folding technique says, right? The next method is folding at the boundaries. In folding at the boundaries also, we first divide this into several partitions. Like this we divide into partitions. Same, let partition size is 3. 1, 2, 3, 2, 0, 3, 2, 4, 1, 1, 1, 2 and 20. Okay. But later for adding we'll do something differently. What we do in the sense, see this is the first, this is one partition, this we will keep as it is. The second partition, no, this we will not treat as 203, rather we will treat as 302. This we will come from least most significant digit to least significant digit 1, 2, 3. But here we will come in the reverse direction. So this 2 not, we will not see this as 203, we will treat as 302. Then the next one we will consider 241 as it is. But then this one we won't treat as 112, rather we treat as 211. Okay. This one we will treat as 20, but after this there is nothing, so we will leave it. Okay. Now we will add all these things 123 plus 302 plus 241 plus 211 plus 20. As a result, what you get? 897. So that is the address, right? So that is what explained here. So in shift folding, for each partition, we take each partition and we just add it. Whatever the result to that location, it will be mapped. Whereas in folding at the boundaries, we take for each partition, but for every other alternate partitions, we will change the direction. This will be treated as 1, 2, 3, but this will be treated as 302. This will be treated as same 241, but this will be treated as 211. Okay, and this is treated as 20. Okay, so that the result what you get is 897. Okay, so you can add and check. Okay, it is 123 plus 203. It is not 203. It is 302 plus 241 plus 112 plus 20. What is that? 3 plus 2 5, 5 plus 1 6, 6 plus 2 8. Okay, 3 plus 2 5, 123, right? 3 plus 2 5, 5 plus 1 6, 6 plus 2 8. But it is, but what should be the value? The value should be 897, right? One minute. So 123 plus 302 plus 241 11 plus 20. Yes, yes, the sum is 897. Okay, I think somewhere we are making mistake. So 123 plus 302 plus 241. Yeah, this is 211. Sorry, this is 211. Okay, plus 211 plus 20. Okay, so what is that? 3 plus 2 5, 5 plus 1 6, 6 plus 1 7, right? 4 plus 2 6, 6 plus 1 7, 7 plus 2 9. Okay, 3 plus 1 4, 4 plus 4 8. So it is 897. Okay, 897. So that is how you got this 897, right? Fine. Okay, so now let us discuss some more examples before going for linear probing and other things. So there are two ways of handling overflow, as we already discussed. So one is called as linear open addressing. So under linear open addressing, we have several techniques like linear probing, quadratic probing, rehashing, and another technique is called as chaining. So these are the broadly the two methods of handling overflow. So let us say, for example, here we are discussing these identifiers. These are the identifiers which we want to map into hash table. Okay, what are the, so this program let us not discuss, but this program's output is explained here, right? So these are the possible identifiers, and the hash table size is 13. Hash table size is 13, and these are the identifiers. What are the identifiers? For, do, while, if, else, and function. Now how this what you call these values are calculated, in the sense this is this is nothing but this 102 is nothing but the ASCII value of F, and this 111 is nothing but the ASCII value of O, small o. This 114 is nothing but the ASCII value of R. All these were added. As a result, what you get is 327. This is X. Now this X is, now table size, hash table size is 32. So what here we are doing is 32 modulo 13. 32 modulo 13 is nothing but 2. Okay. Similarly for do, D, D, do is some loop. Okay, do loop, do while loop, right? So D ASCII value is 100. O ASCII value is 111. So if you add it, what you get? 211. So 211 mod 13 is 3, right? So on and so forth. Like that we are doing this. So here you can see the, what you call, you can see the ASCII table. I will just for reference. So you can see here, say F O R, we will see 102, 11, 111 and 114. So you can see A B C D E F. F is 102. Okay. O is 111, right? R is 114. Okay. So this is how it was. You got those values, right? And then it is mapped. So this is how it is mapped, right? Now you can see there are some collisions. Here there is a collision. Here there is a collision. So when there is a collision, what you should do? You should go for linear probing, or you have to go for any other techniques. Okay. So in linear probing, what we do when there is a collision, if the hash function at this location, if it is creating a collision, then increment that location and check. It is go to the next location and check. How long you should do? Until the table is not full. Okay, right? So that is what is called as linear probing. So here previously we discussed this a cause, a character, all these things, right? There we have discussed with two buckets. Okay, here we are discussing with one. There we are discussed with two slots per bucket. Here we are discussing the same thing with only one slot per bucket. With only one slot per bucket. Okay. Now if you see, there is only one slot in a bucket, right? So this is only single hash table. Okay, it is shown in two halves. So a cos a is mapped to, so now the hash function is this. A is mapped to 0th location, B is mapped to first location, C is mapped to second location, D is mapped to third location, E is mapped to fourth location, F is mapped to fifth location, so on and so forth, right? And A, B, C, D, E, F, G is mapped to sixth location, H is mapped to seventh location, up to Z is mapped to 25th location. Okay. Now you see A cos, it will be mapped to which location? 0th location. Fine. It is successfully mapped. Now the each bucket contains only one slot, not two slot. Okay. Second, now you want to, what do you call? Now you want to map. See, these are the bucket numbers. Okay, 0, 1. Now we want to map A to I. But already A to I also should be mapped to 0th location. But already 0th location is occupied by A cos. So if you use linear probing, you check the first location. As of now, the first location is empty. So A to I comes here. So A to I comes here, right? Okay. Next, character. Next, this particular thing, character. Okay. So character, it is supposed to map to second location. A, B, C. C is 2. Okay. Second location is empty. So it is mapped. It is mapped to second location. Okay. Next is define. It starts with D. It is supposed to map to third location. It is empty. So it is mapped to third location. Next is EXP. EXP starts with E. It is supposed to map to fourth location. This location is empty. So it is mapped to fourth location. Next is seal. Come to seal. This seal is should be mapped to second location. But actually second location is char. So linear probing, what it will do? It will check the third location. This third location is empty. No, define is occupying. Then it goes to the fourth location. Is it empty? No, exp is occupying. So seal is given fifth location. Okay. Now see cos. Cos also supposed to map to second location, but second location already char is there. So linear probing checks to the next location. Third location, is it empty? No. So go to the fourth location, is it empty? No. Go to the fifth location, is it empty? No. So sixth location is allocated for cos. Okay. Next is float f. F is supposed to map to fifth location, but in fifth location already seal is there. So linear probing says go to the next location. 6. Is it empty? No. So go to the seventh location. So floor is given this location. Float is given this location. Next is at all. At all starts with A. It's supposed to map to zeroth location, but zeroth location contains A cos. So linear probing says go to the next location. Is it empty? No. So go to the next location. Is it empty? No. Go to the next. 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 So at all is allotted to 8th location. Right. Next is floor. Starts with F. It's supposed to map to 5th location. 5th location already seal is there. So according to linear probing, go to the next location. 6th location is not empty. So go to 7th location. This is also not empty. Go to 8th location. This is also not empty. So go to 9th location. So floor is mapped to this location. Okay. Now C time. It is a starting character is C. So it is supposed to map to second location. But second location contains char. So linear probing says go to the next location. Third location not empty. Fourth is not empty. Fifth is not empty. Sixth is not empty. Seventh is not empty. Eighth is not empty. Ninth is not empty. 10th is not empty. 10th is empty. So it comes to this location. Okay. Now what is this? This column says how many bucket you need to search to identify a particular value. If you want to search A cos, just to only one search, because A means what? Zeroth location, and in zeroth location it is already available, so it's only one search. A to I we need to search, because A means it maps to 0, but from 0th location A cos is not there. In the first location it is there, so after 0 you will be searching first location. So the algorithm will map to 0, but then it is not there, so you should go to the next location and you should check is it there. Yes. So total it needs two locations to search. For character, how many search we need? C maps to second location, so directly in second location you can get it, only one search. For define we need how many search? D maps to third location, so directly in third location it is available, so only one search. For exp we need how many search? It E maps to fourth location, it is in fourth location, so we need only one search. Seal needs how many search? C maps to second location, but in second location character is there, so go to the third location. Is it seal? No. Go to the fourth location. Is it seal? No. Go to the fifth location. Is it seal? Yes. So how many locations we have searched? 1, 2, 3, 4. So totally there are 4 searches. Okay. Similarly for cos, C maps to second location, but it is char, one search. This is defined, second, no. This is exp. Is this is cos? No. Next is fifth location, is this is cos? No. Fifth is this is cos? Yes. So it needs 5 searches. Okay. Next, float, it maps to fifth location, but in fifth location we have seal, so already one is done. Then go to sixth location. Is it float? No. 2. Then seventh location, is it float? Yes. So 3 searches. Okay. Then at all, it is actually the algorithm will map to 0th location. 0th location, is it at all? No. So 1. Next location, is this at all? No. This is a to 8, so 2. Next location, is it at all? No. So 3. Next location, is it at all? 4. No. Is this is at all? No. 5. Is this is at all? No. 6. Is this is at all? No. 7. Is this is at all? No. 8. Is this is at all? Yes. So how many searches? 9 searches. Similarly for floor, if you calculate, there will be 9. There will be 5 searches. It starts with fifth location. Okay. Is this is no. 1, 2, 3, 4 and 5. Similarly for C time it is 9. Okay. So totally now here we have how many items, in the sense 11 items. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And these 11 items, different items need different amount of search. If you add all these things, you will get 41. 1 plus 1, 2, 2 plus 1, 3, 3 plus 5, 8. Okay, 18 plus 8 is 18. 18 plus 8, 26. 26 plus 2, 28. 29. 29 plus 7. 29 plus 7, 36. 36 plus 5 is 41. Okay, so the average number of buckets examined is 3.73. Okay, actually it is a high number. Actually this is a high number. So here we are discussing the drawback with linear probing. This is the problem with the linear probing. With linear probing, the performance of hashing will decrease, because previously we have discussed that using hashing, any item can be searched in order of 1 times, but it is taking order of around 4 times. Okay, so this is the problem with linear searching, linear probing, because the similar items will be clubbed in one direction, one place, one locality. So that is also called as Coles phenomenon. This problem is there with linear probing, right? So there are many improvements suggested. You can also do quadratic probing. In quadratic probing, just it says that instead of using a linear equation, use a quadratic equation. Okay, and there is a technique called rehashing. Rehashing says that whenever there is a collision, you use some other hash function. So already we are using the hash function k modulo 10. But for a particular key, if k modulo 10 is creating collision, then change the hash function. Instead of using k modulo 10, you try using another hash function. 3 into k plus 1. Use this function modulo 10. Okay. I mean, you should have a couple of functions. You should have many functions, f1, f2, f3, like that up to fm. And whenever there is a collision, you try using another function. Okay, and whichever the function that does not create the collision, use that, right? But the disadvantage of this method is you have to maintain many functions, and you should know which hash function you are using for which identifiers. All these things should be maintained. That's the drawback with this method. Okay, and chain rule, what it says, or as we have discussed already, it says that uh, a single location can be mapped to several key by using linked list. Okay, so here we maintain an array of pointers. If you discuss this previous example using chain, what will happen? All the identifier that starts with a will come in 0th location. So 0th location, there will be a pointer that will point to a cos next will point to a to I next will point to a all. Currently at first location there is nothing, so it will point to null. Second location, it will point to characters next will point to seals next will point to cos, and cos next will point to c time. Third location, it will point to define, fourth will point to exp, fifth will point to float, and float's next pointer will point to float, so on and so forth. Okay, so this is how the concept of chaining works. Fine, let us stop here. So that's it about hashing. Thank you.